Hi all, for this video lesson I'm going to show you some of the examples on final year and also test questions for Fourier Transform applications. This is from past year test in 2007 and 2008. Signal xt shown in figure Q1b here has gone through two operations given as ops1, which is operation 1, and ops2 independently. As a result, they produce two signals, yt and also zt. Okay, so given the form of the xt is this triangle shape, and given the Fourier transform of these signals for yt, okay, and also zt, yt, the pair of Fourier transform is given as y omega equal to x omega multiplied by exponent negative j omega divided by 2. And zt is the Fourier transform for zt, which is z omega, is equal to 2x2 omega. For the first question, name the two operations ops1 and ops2 by referring to the Fourier transform properties table. And for question number 2, you need to sketch yt and also zt. Okay, in order for you to determine this operation, we need to look back at the equation for the Fourier transform here for y omega. So given that y omega is actually x omega multiplied by exponent negative j omega over 2, and zt, the Fourier transform is z omega, which is 2x2 omega, meaning that z and y is the Fourier transform for xt that has gone through certain operations. So what are the operations? So we need to refer to the Fourier transform properties table. So when I refer to the Fourier transform properties table, and I found out that the closest form to the given question, which is y omega equal to x omega multiplied by exponent negative y omega is equal to x omega multiplied by exponent negative j omega over 2. And the closest form here is time shifting operations. And another one for zt, given that z omega is equal to 2x2 omega. So if you compare to the time scaling, this is the closest form to the Fourier transform for zt. First question, name two operations ops1 and ops2. We put like this, ops1 yields y omega equal to x omega exponent negative j omega over 2. So basically this is a time shifting. It is a time shifting operations with t naught equal to 0.5. So when t naught here equal to 0.5, we will get in terms of xt, which has been transformed to x omega, we will get x omega exponent negative j omega 0.5. So omega over 2 is 0.5. So for operation 2, ops 2 yields equal to 2x2 omega. So basically this is a time scaling with a here is equal to 0.5. So why is a here 0.5? This is because when this one is 0, a here is 0.5, it means that 1 over 2. Okay, so omega divided by 0.5 is 2. Okay, 1 divided by 0.5 is 2, so it will become here 2 omega. Okay, so this is basically an amplitude scaling. Okay, so we answered already question number 1. So question number 2, you need to sketch yt and zt. So based from the operations that we have found out, we can basically derive back the time domain function for yt and also zt. For yt, okay, yt is actually xt with time shifting t naught equal to 0.5. So when we want to write in terms of time domain and in terms of xt, so yt here is equal to xt minus t naught which is equal to x t minus 0.5. So from here we can draw the yt. We know that xt is given as a triangle shape, triangle signal with the amplitude 2, and the time here is from -1 to 1. Okay, so from here we draw another triangle, but the triangle has been shifted by 0.5. So for yt, it has been shifted by 0.5, and the signal here will start from -0.5 to 1. Okay, and the amplitude remains the same. This is okay. Now we already answered question 2 for yt. One is zt. So zt is xt with time scaling a equal to 0.5. So when we write zt, zt is equal to x at, which is equal to x 0.5. Okay, so if you perform a Fourier transform for zt here, you will get z omega equal to 2x to omega. Even though there is an amplitude scaling here, this is basically from the time scaling in time domain. Okay, because when a is equal to 0.5, again when you divide 1 equal to 0.5, you will get 2 here. Okay, so from the original signal here, you can plot zt. So zt is time scaling, which is 0.5. So using your knowledge in the chapter 1, we can write here as tau. So tau equal to 0.5 t equal to tau divided by 0.5. Okay. Now, when you want to find t, so when tau, we will refer to the original signal here. So when tau equal to -1, t equal to -1 divided by 0.5 is -2. Tau equal to 1, t equal to 2. Okay, so this the new time starts from -2 to 2. So from here you can draw the new triangle which starts from -2, and the amplitude remain the same because now we are talking about time domain. Okay, even though when you see here in the spectrum or in the frequency domain, the amplitude scaling here will become 2. Okay, but this one is time domain, so there is no amplitude scaling when you when you perform the inverse Fourier transform. It's only time scaling. Okay, so you label this as zt. Okay, so this is the answer for exercise 1. Exercise 2, this is also comes from past year question, but I can't remember. I think it's before 2013. Okay. Figure A below shows a transmitter-receiver system. Okay, transmitter and receiver system having an input signal x, and the Fourier transform of xt is given in figure B. So this is the spectrum of xt, and gt here is an ideal low-pass filter with a cut-off frequency of omega c equal to 500 and gain equal to 1. And bt is the output signal from transmitter system that is then received by the receiver system. ht is an ideal high-pass filter with a cut-off frequency of omega c equal to 100 radian per second and gain equal to 1. So I repeat again, for this whole system, we have xt as the input, okay, and the dotted box here shows the transmitter system. And then this xt is modulated with carrier frequency, carrier signal number 1, which is sig1t, with the signal cosine 500t, right? Then the modulated signal here produces at, And then this AT goes through the low pass filter. So GT here is a low pass filter with omega C equal to 500 radian per second. Okay, so first of all, you need to understand the diagram, okay, before you jump to the question. And then from output from the low pass filter or from the transmitter is BT. So basically BT here is transmitted. Okay, so when BT is transmitted and then it arrives at the receiver, and here is another mixer because this is a modulation process. So BT here is demodulated. Sorry, this is not modulation process. At the receiver, it is demodulation. But basically, the process is the same as modulation. So the demodulation process, also BT is demodulated with carrier signal number 2, which has cosine 500t. And then it produces DT, and this DT goes through HT, which is an ideal high pass filter. So this is HT. So remember, when I say ideal means that the shape of the filter is sharp. Okay, the corner has a sharp corner. And the cutoff frequency here is omega C equal to 100 radian per second. Okay, and gain is also equal to 1. So this is the given shape of X omega. So you do not have to panic when you see the shape. Given any of the shape here, it's okay because you do not have to perform much calculation. For Fourier transform question, you just have to understand the concept. You do not have to perform any, most of the question, you do not have to perform calculation. Okay, but you have to understand the concept, what happens when the signals is being modulated and also demodulated and goes through any filter. Okay. Okay. And the equation here, okay, I put the diagram here again for easy reference. So the equation here is cache spectrum of A omega, okay, B omega, D omega, and Y omega. So where do these terms come from? Okay, so we refer back to the diagram here. A omega is basically comes from Fourier transform of AT, okay, which is the output signal from the modulation of XT with C1t, right? And B omega comes from BT. Okay, the Fourier transform of BT is B omega, which comes from the output of the low pass filter. Okay, so the first question here, remember when I put here is low pass filter, the first filter here. Okay, low pass filter, and then it produces BT. So BT transform using Fourier transform to frequency domain, it becomes B omega. And then D omega comes from this DT, okay, which is the demodulation between BT with C2T, right? And finally, Y omega, which comes from YT, is the output of DT that goes through the high pass filter HT at the receiver. So you notice here that the mark here is the mark given here is 12 marks. Okay, it means that each of the sketch here will contribute to 3 marks. Okay, right. Understand the concept of modulation in order to plot A omega. So we know that AT, okay, AT comes from XT modulation. Of course, it is multiplied with 500t, cos 500t. Like I say, however, when any signal multiplied by cosine signal, you can use the modulation properties. So from the modulation properties on the table, okay, from the table, you can see that if ft multiply or modulate with cosine omega naught t, the Fourier transform here, okay, will become 1 over 2 f omega plus omega naught plus f omega minus omega naught. Okay, so from here we can get A omega equal to 1 over 2 x omega minus 500 plus x omega plus Okay, so either minus first or plus first is okay. Okay, so maybe I follow the table here. Okay, the table here. So I put plus first. Okay, and then minus 500. Okay, so remember that you need to show how you obtain the result. Okay, how obtain your answer. You cannot just show the answer without showing the steps. Okay, otherwise it will be wrong because you know it doesn't look convincing that you how you obtain the question the answer. Okay, so again, x omega is like this. Okay, so we know that x omega here is being modulated by cosine. So x omega here will be shifted to 500 here and also negative 500. And the amplitude of x omega will be divided by half. Okay, so that is a omega. So from here, we can draw a omega. Which has the same shape. So like I said, because this is because we cannot put the correct scale, so we put like this, M shape. Okay, for the signal. I hope you can draw it better than me. So here should be 2 and here should be 4, which is half of x omega. So this is a omega. And if the origin here is 0, so this one should be negative 500. This one should be 500. So make sure you label as well at the x and y axis. And this is 450. This is 550. This is negative 550 and this is negative 450. Okay, so now you answered question 1 for a omega. Omega, we have to refer back to the question. So the question said that BT is the output from the from AT that goes through the low pass filter. So low pass filter is given as, okay, if you remember the low pass filter, it's given as the shape of low pass filter. Okay, it's something like this. And the cutoff frequency is negative 500 to 500. Okay, so refer back to the question. For the first GT here is given as ideal low pass filter with a cutoff frequency of omega c equal to 500 radian per second and gain equal to 1. It means that the amplitude is equal to 1. Okay, so basically this is G omega, which is the low pass filter, the spectrum of GT. Okay, so from here, you can imagine that A omega here will go through G omega. Okay, so if you compare the frequency here, we know that the signals here will be truncated at 500. So only signals from negative 500 to 500 that will go through this low pass filter. Okay, so from there we can draw B omega. Okay, we know that A omega goes through G omega, so the signal from that is outside negative 500 and 500 will be truncated. So for B omega, the signal will become something like this. And the gain is the same. So it means the amplitude for B omega will be the same as A omega. So it will be something like this. Okay, this one is 2, this one is 4. So this one is B omega. This is omega. And here, the frequency here is from negative 500. Okay, to 500 because that is the cutoff frequency. Okay, means that only this part of the signal, Okay, let me color here. Okay, only this part of the signal will go through the low pass filter. To draw, sketch the spectrum for D omega. So we know that D omega is BT, which has been demodulated with carrier frequency, carrier signal number 2, C2T, cosine 500T. Okay, so I will draw here again B omega that we have obtained before for your reference. So for dt, it's better for us to write the equation first. So dt is equal to BT multiply by cosine 500t. So when we transform into Fourier transform, we will get d omega, which is equal to 1 over 2. This is using the modulation properties. B omega plus 500 plus B omega minus 500. Okay. So again, when we see here d omega is the amplitude for d omega is actually half from b omega. Okay, so the amplitude here will be divided into half. So 4 will become 2 and 2 will become 1. So now you can draw d omega, and also each of these component in b omega will be shifted to 500 and negative 500, and this part also will be shifted to 500 and also negative 500. So there will be 4 components. So let's say we start from this part first. Okay, so now negative these components, okay, the signal starts from negative 500. So when it is shifted to 500 to the right, okay, using this equation, shifted 500 to the right. So this negative 500 plus 500 will become 0. Okay, so the first signal here, this one, for this one. Okay, this is 1, this is 2. Okay, so this is 1 should be 50. Okay, because the width of the signal is 50. Right. So the second one, this signal also, but the signal is shifted to 500 to the left, because this is plus 500. So 500 to the left, it goes further to the negative side. So negative 500 plus negative 500, it will become 1000. Okay, so we put something like this to show that the axis here should be longer than this, okay, than what we write. This is not really a correct scale. Another signal of these components which has been duplicated. Okay, and this one is negative 1000 and this is negative 550 because the width of the signal is 50. So another signal here is this component, okay, from 450 to 500. So first we take this part, okay, this 500, okay, this scale. So 500 here, first it will be shifted to the positive side. So 500 plus 500 to the right. Okay, so we have another components of this. Okay, so this one is 1000. Okay, 500 plus 1 is 1000. This one should be 950. And this signal, okay, when we shift it by 500 to the left, means to the negative side, so we minus. So we minus 500, this 500 will become 0. Okay, so this one is like this. So make sure that you are careful here. Okay, you should add, let's say you take this part. Okay, so you just use this part to add or minus 500. Okay, and then you know that the width here is 50, then from there you can draw the signal. Okay, so this is negative 50. So now you have answered d omega. Okay. Okay, to answer the final question, y omega. So y omega is dt that goes through the high pass filter with omega c equal to 100 radian per second. So you have to draw the high pass filter to show that you understand the concept or you know how to get the final signal. Okay, so high pass filter here is given as ht, which the spectrum is called h omega, and the cutoff frequency is omega c equal to 100 radian per second. So it's somewhere here. If we refer to the scale for the omega, it will be somewhere here. Okay, and this is negative 100. Okay, so from here we know that whatever signal that has frequency above 100 will be retained, and whatever or also above negative 100, and whatever signals that is in between -100 and 100 will be eliminated. So this part will be eliminated or will be removed, and this part will be remain. So from here, you can draw the final answer for y omega. So y omega will become this y omega, and of course you draw like this because the sketch should be longer than this. So only this part. So draw something like this. Okay. So like I said, it doesn't involve any much calculation, okay, for Fourier transform, but you have to understand the concept that when you modulate and demodulate, the signal will be shifted and also doubled from original, and also the amplitude will be divided by half. Okay, and when the signals go through the low pass filter or high pass filter, you have to notice, you have to identify the cutoff frequency, and also identify which part of the signal that will be removed and which part of the signal that will be retained. So you label. So this is y omega. Okay, all right. So now you answer question number 1. We have another question here, which is question number 2. Now for question 2 is quite challenging. You need to design a receiver system in order to get the spectrum of y nu omega as shown in figure C. So now the question required you to design a receiver system so that you can obtain this new signal, new spectrum. To do this, determine the new mathematical expression of signal C to T. So this is signal C to T, which is the part, this carrier part at the demodulator, or at the receiver, and multiplied by BT, and draw the new spectrum of H nu. Okay, means that this HT is a new filter. Okay, so we need to know what is that new filter to replace the original HT. So the spectrum of this new filter is called H nu omega. And your answer must also show the new spectrum of D nu. So you need to show also the output from the demodulator here, or the demodulation process, which is DT. Okay, so what you have to show here is first determine the new mathematical expression of signal C to T. So this is 1, and then draw the new spectrum of H nu. This is 2, and then your answer must also show the new spectrum of D nu. So this is 3. So basically it will contribute to 8 marks. Right? Okay, so in order to get the frequency between, because when we see y nu here, the frequency is between -25 and also 25. So the new C2T here, new mathematical expression of C2T here, must consider that frequency. So we know that 450 plus x is equal -25. Okay, so we need to find this x. So why I put 450 here? We want to shift this 450 here to 25. Okay, so that it goes to 25 here, and then from here x is equal to 475. Like I said, it is quite challenging. It needs you to think and also understand and to try and error. Okay, if you can understand this, and maybe you can just shift like this. Okay, shift the signals and find out how the combination of the signal, okay, or the summation of the signal can produce box like this. Okay, a square signal like this. Right. So from here, C to T is equal to cos 475t. Okay, so now when you already find out C to T, okay, you can determine D omega. Okay, so we know that BT is equal to BT cos 475t. So from here, we can write the expression for D omega, which is 1 over 2 B omega minus 475, or you can put plus first, it's up to you, plus B omega minus 475. Okay, so from there, we can draw the new D omega. So D omega be something like this. Okay, we refer back to B omega. So we know that we have two components. So we plot the first component first, which is from negative 500 to 450, negative 450. So negative 500 here, you add with 475. It means that we want to shift it to the right. So you add with 475. You will get negative 25. Okay, negative 25. So it will be something like this. Okay, so the signal will be from negative 25 to 25 because the width of the signal here is 50. Okay, and then another one, this component also, you minus with negative 475 to show the shift to the left or to the negative part. Okay, so it become something like this, from 975 to 925. Okay, and the amplitude here will be 1 and also 2. Okay, and then another part here is this part. Okay, so this part is also shifted to the right and to the left by 475. Okay, so again using the same calculation as I taught you before. So the first part here is like this. So this is 925 to 975 because the width here is 50. And another one should be like this. Okay, which this one is we call that bertimbang. It's like a summation of two signals. This is superimpose signal. Okay, so there are two signals here overlap. Okay, is the new omega. Okay, so basically you have answered the question. Okay, you you haven't answered the full question. Basically you have answered two questions here. You have determined the mathematical expression of C to T. Okay, from there you will get d omega, and you draw d omega here, and now we have to determine the h nu so that we can get y nu. Okay, so if you imagine here these two signals overlap, okay, and when these two signals overlap, it means that it is added together. Okay, because this is the addition of two signals. And then these signals, this part of the signals, when you add this part of the signal, it will become straight. Okay, and this part of the signal, when you add this part of the signal, when you add this part of the signal, it will become straight. Okay, and then the h nu should be something like this, because we know that y nu is from negative 25 to 25. So it means that h nu should be low pass filter. Okay, low pass filter. And the frequency here should be, omega c should be more than 25. So if you want to write in terms of equation, h nu omega here is 1 rectangle omega divided by 2 omega c. Like I said before, you have to memorize the equation for the low pass filter. So omega c is bigger than 25, should be bigger than 25. Okay, so it can be any numbers. Okay, other than 25. Sorry, this should be 25. Okay, it should be 25. So this one is h nu omega. So what about amplitude? Okay, because here is 3, so and here is actually the addition of two signal. So if we consider the amplitude of these two signal from, let's say, let me highlight this signal. Let's say you want to add this part. Okay, so this part of the signal. Okay, so when you add with this line here, okay, basically you will let's say you add here, point here 1, you add plus 2 is equal to 3. Okay, so that is why y nu here is equal to 3, and for this part 1 plus 2 here is equal to 3, and for this ramp part here, okay, RAM part here, RAM signal, okay, we will cancel out each other and it becomes straight. So that is why Y new here will become straight, and because of that, the amplitude here should be 1 only. Okay, you don't have to multiply by 3 or anything, because when you sum up these two, when you add these two signals, it will become 3. Okay, so now you answered all of the question for exercise 2. Now for exercise 3, this comes from past year final exam question in 2016 and 17. In the communication systems that have multiple independent transmitters and receivers, a frequency multiplexing is a transmission. Figure Q4C, which is the figure, illustrates the frequency multiplexing scenario where two signals, M1t and also M2t, are transmitted simultaneously on the same channel. Right. And the signal at point B here is the multiplex signal, okay, which is the summation of M1 signal and also M2 signal, which has been modulated with 5100 pi. And then the signal at point B is the multiplex signal, which is later being modulated with the carrier signal at frequency 30,000 pi per second. The modulated signal at point C here is then transmitted over the channel, and the Fourier transform of M1t and M2t are given as follows. So M1 omega here and M2 omega here is the Fourier transform for M1t and M2t. So I repeat the question again. Basically, there are two signals, M1t and M2t, which has independent transmitters and receivers. However, the system uses a frequency multiplexing to sum this M1t and M2t. So M2t goes through the modulation process first, and then sum with M1t. And at point B here is the multiplex signal, and then this multiplex signal is modulated with the carrier signal to cosine 30,000 pi t, and will give you modulated signal at point C, and before it is being transmitted of the channel. And M1t, the Fourier transform of M1t is given as M1 omega, which is the sinc function multiplied by rectangle function. Okay, and M2t is a rectangle function. So when you see this, please do not panic. Okay, this is actually easy if you understand on how to obtain M1 omega shape. Okay, so now the question here is sketch the spectra of M1 omega. Okay, so which is M1t transformed to the frequency domain, and M2t transformed to the frequency domain. Both are using Fourier transform. Points A, B, and C. So notice here it gives you 10 marks, okay, for the answer, for all the answers M1 and M2 omega at point A, B, and C. Okay, so first we need to draw M omega. Okay, before it goes to point A, we need to draw M1 omega. So we know that M1 omega is given as sinc function multiplied by rectangle function. So M1 omega is a sinc function multiplied by rectangle function. Okay, so now you need to know how to draw sinc function. Okay, so basically sinc function here, when you want to draw, we know that the sinc function here is something like this. So what you need to know is the origin here and also this part. Okay, so this is sinc omega divided by 2500, which is M1 omega. Sorry, this is sinc function, not yet M1 omega. Okay, the frequency here should be negative 2500 pi and 2500 pi. Okay, so how did I get this value? Okay, so now remember back the original sinc function. Okay, and also you can refer back to the list of formulas, and you can see the equation of the sinc function and how it plots the sinc function. Okay, so let me draw here with another ink here. So let's say here we have, let me show you how to draw the sinc function. Let's say here we have original form, which is a tau sinc omega tau over 2. So the drawing for this is like this, and the value of amplitude here is a tau, and the value of the frequency here is 2 pi divided by tau, and this one is negative 2 pi divided by tau. So you mesh here with the value of the equation here. Okay, so it should be 2 multiplied by pi divided by tau. Okay, so from here you can mesh that the value for the frequency here should be 2500, okay, divided by 1, but actually 2500 must be multiplied by pi, just like this. Okay, so basically when you are not sure how to draw this, you refer back to the list of formulas. Why? Because in the list of formulas, it shows you the shape and also the original, we call it original equation for that function. Okay. Okay, now this sinc function here, which is this, okay, is multiplied with rectangle function. So rectangle function, also you need to master how to draw the rectangle function. It has 1 as amplitude here. This is rectangle omega divided by 5000 pi. So 5000 pi here at the denominator here means that the signal is from 2500 pi and to 2500 pi. So from negative 2500 pi to positive 2500 pi. Okay, so basically the width here should be 5k pi. Okay, and then from here we know that when these signals multiplied by the rectangle function, so the signal that is remain here is whatever between 2500 pi and 2000 whatever signal remain here is the signal between negative 2500 pi to 2500 pi. It's just similar like filter, okay, filter process. So outside of this frequency is filtered out. Okay, so what we have now is actually only the dome part here, okay, with frequency 2500 pi to 2500 pi, from negative to positive 2500 pi. So this is M1 omega. So once we obtain M1 omega, now we can perform the modulation here so that we can obtain the spectra of M1 omega, okay, at points A, B, and C. Okay. Okay, so M1 omega here is the answer for the first answer, okay, before it is being summed with M2 omega. Okay, so we want to find M2 omega first. Okay, so M2 omega is given as right here, M2 omega is given as rectangle omega divided by 10,000 k pi. Okay, so from here we can draw M2 omega. Okay, this one should be negative 5k pi to 5k pi. Okay, because the denominator here indicates the width of the rectangle function here. So this is M2 omega. This is omega. Right, so M2 omega is being modulated with 2 cosine 15,000 pi t. So we put here at point A, we know that M2t multiplied by 2 cosine 15k pi t, okay, which is 15,000. So okay, so this is equal to 2 M2t cos 15k pi t. So let me use the terms MA omega, M2A omega to show, MA omega to show the new spectrum after the modulation process. Right. So using modulation, MA omega, which is the spectrum of M2 after being modulated at point A here. So MA omega is equal to, this is using the modulation properties, 1 over 2, and then this is 2 here, M2 omega plus omega naught. So omega naught here is 15k pi. So this one is plus 15k pi plus M2 omega minus 15k pi. So for this, we will get M2 omega plus 15k pi plus M2 omega minus 15k pi. So we know that M2 omega is rectangle function. So basically this will become rectangle omega plus 15k pi divided by 10k pi plus rectangle rectangle omega minus 15k pi divided by 10k pi. So we can see that basically the rectangle function has been shifted to the left and also to the right, and the amplitude here has become half. Okay, half. However, because here we multiply by 2 here, so basically the amplitude here will be is the same. Okay, this one should be 1. So now we draw MA omega. Okay, so I hope you can draw. Okay, so let me draw in another page here. So MA omega will become 2 rectangle function, and the origin here should be negative 15k pi. Okay, because it has been shifted by negative 15k pi and also 15k pi. Omega, this is MA omega. The amplitude should be 1. Okay, so you label the signal, okay, every part of the signal. So this one is negative k pi, this one is negative 20k pi. Okay, because the width of the signal should be 10k. This one 10k pi and this one 20k pi. Okay, so now you answer MA omega at points A. Okay, so now at point B is the multiplex process between M1 and also M2T that has been modulated. Basically, we already know M1 omega, and also we have plot MA omega, which is M2 at point A. So we call back M1 omega here. Let me draw here. M1 omega is dome shape with with the frequency from negative 2500 k pi to 2500 k pi. This is M1 omega. So when you want to plot the point at B here, let me put it as MB omega. Basically, is the summation of M1 omega and MA omega. So what I put here is omega is equal to M1 omega, which is this, okay, plus MA omega, okay, because of the summation here. So you need to know also the symbols here, whether it's summation or multiplex, or if the arrow here show minus, then you know that you have to minus that signal. But this one is there's no sign here, meaning that it is a normal summation with it, which is another. Okay, so the plot here become like this, in which you have to draw both signals MA omega and M1 omega. Okay, and there's an M1 omega here. Okay, from negative 2.5k pi to 2.5k pi. This one k pi to 20k pi. This one is from negative 10k pi to negative 20k pi. right? And the amplitude here is 1, and this is MB omega, right? Okay, so now you answer a question which asks you to sketch a spectra at points B. Another question is sketch the spectra at point C here. So it means that MB omega here is being modulated with 2 cosine 30,000 pi t. So let me answer here on the page. So at point C, it is basically let me put MB omega in time domain as MBT multiply by 2 cosine 30,000 pi t. So this is MCT. Okay, so I put it as MCT. So basically for MC omega, which is the spectrum of MCT, which has been transformed to frequency domain using Fourier Transform, is equal to 1 over 2 multiplied by 2. So this is MB omega plus 30k pi, okay, because this is the omega naught. Okay, so it means that this is the shifting for this MB omega plus MB omega minus 30k pi. Okay, so cancel out, you will get omega plus 30k pi plus MB omega minus 30. Okay, so basically you don't have to write the whole equation, okay, because it will be long. As long as you understand the concept, okay, you can leave it in terms of MB. From the previous page, recall back that we already know MA omega, which is at this point, okay, and then M1 omega, which is at this point, and then MB omega, which is at this point before it is being modulated. So this is how MB omega looks like. So when it is modulated again with cosine function here, so basically it will the spectrum of MB omega here will be double, okay, and will be double and also shifted to the frequency by 30k pi. Okay, so if let me draw again MB omega in the next page here. So MB omega here is like this. Okay, we have dome, we have rectangle, okay, with the origin of 0. This is 0.5k, from negative 2.5k to 2.5k pi. This is from 10k pi to 20k pi, and this is from negative pi to negative 10k pi. Okay, this is M. So when we want to draw MC omega, we consider the shifting by 30k pi and negative 30 pi here. Okay, so we draw MC omega. So again, like I say, you do not have to write in terms of the original signal, which is M1 omega and M2 omega. You can leave it in terms of MB omega, because what matters now is the spectrum. Okay, the question doesn't ask you to write in terms of mathematical expression. Okay, the question asks you to sketch the spectra, or sometimes the question asks you to express graphically, which is sketch. Okay, so first we take this part. Okay, remember that all these three parts of the signal will be doubled. So this first part, which is the dome signal, will be shifted by 30k pi and negative 30k pi. Okay, so this is here, and should be what matters here is the origin here, negative 30k pi, 30 pi. Okay, you can also label, okay, at the start of the signal and the end of the signal, which you consider the width of the signal. So the width here is 5,000. Okay, 5,000, and this one from the origin is negative 2.5K. So here should be something, you calculate by yourself, right? Okay, and then the rectangle here, okay, the rectangle here, also you should consider the origin, okay, so that it's easier for you to plot. Okay, this one should be 20 to, this one should be negative. Okay, so this part here will be shifted to the right and to the left. Okay, so it should be, when 15K plus 30K will be 45K. This one will be like this, 5. Okay, and another one will be shifted to the left. Okay, to the left, 15K pi minus 30 will become negative 15. So this one will be here, okay, pi. Okay, and all the amplitude here remain 1. Okay, because you have done the modulation process just now, because the modulation has to multiply 2 cosine. So basically, it will remain 1, right? And this part of the signal here is also double. So first, negative 15K here is shifted to the right by 30K. So it will be here. Okay, so this one will be 15K pi, and another one will be shifted to the left by 30K, means that negative 15K minus another 30K should be negative 45K. Okay, so basically because previous spectrum you have shown all the values for the signal, so for the final answer, even if you show the value of the origin of the signal here, I can accept. Okay, so you don't have to label each of the signal, each of the frequency of the signals starts and the end of the signal here. Okay, you can just label the origin of the signal. The origin means the middle of the signal, or if you want to label here, it also can. Okay, the end and start of the signals. Okay, as long as the x-axis here has values, so that I know that you show the correct answer in terms of shifting of the signal. Okay, so basically you have answered question number 1, right? For question number 2, this is what we call K-bar question, or the higher level order thinking question. Okay, so it can have several answers. So first, as an engineer, what will you do in order to recover back the information signals M1t and M2t at the receiver part? So this is based on your understanding of modulation and demodulation process at the transmitter and also receiver. Okay, so of course, based on what I have taught you, what I've said before, that in order for you to recover back the original signal that you have transmitted, you need to demodulate back with the same carrier function, same carrier signal. Okay, so for this, M1 and M2t need to be demodulated with 2 cosine 3000 t. Okay, 3000 pi t. And second of all, after you demodulate the signal, because this is the multiplex of M1 and M2, so there must be another process which is demultiplex. So to recover back M1 and M2 as an individual signal, we need to use demultiplexer to separate the modulated signal M1t and M2t. And finally, M2t modulated signal here needs to be demodulated back with 2 cosine 15,000 pi t. And finally, after this demodulation, all this demodulation process, we need to apply the band pass filter in order to only retain original M1t and M2t, because we want to remove the double signal. Okay, remember that when we perform modulation and also demodulation, the signal will be double. Okay, so I will write all these answers here. Repeat back. So when you want to recover back the information signals M1t and M2t, basically you have to reverse back whatever process at the transmitter. So this is the process at the transmitter. So in order to recover back, first M1 and M2t need to be demodulated with 2 cosine 3000 pi t, okay, which is the same as this, right? And then first use the multiplexer to separate M1t and M2t, and M2t modulated signal needs to be demodulated back with the same carrier function, which is 2 cosine 15,000 pi t. And finally, we need to apply bandpass filter, because when you demodulate, the signal will be double, okay, many times from here to here, and apply bandpass filter to obtain original signals M1t and M2t. Okay, so that is all for this video lesson. So I will show some more examples, but in terms of writing the proper solution, okay, and I will upload it at the on the e-learning. Okay, so I hope you can see step-by-step solution that I have specifically solved for you. Okay, thank you very much.